Have you ever stopped to think about how we find the best of anything? You know, the best route for a delivery truck, the best investment strategy, or even the best way to train a machine learning model? Well, it's not magic, it's math. So today, let's dive into this incredible field called optimization, where we're going to learn how to find the absolute best answer to pretty much any problem we can imagine.
To make this all feel a bit more real, I want you to picture this as a grand adventure. We're a hiker, okay? And our one and only goal is to find the absolute lowest point in a huge, hilly landscape. This landscape, that's our objective function. It's just the thing we're trying to minimize. Where we're standing, our coordinates, that's our decision vector. Think of those as the different choices we can make. And any fences or boundaries we see, those are our constraints, the rules we have to play by.
So, here's our trail map for the journey. First, we're going to figure out what best even means in this context. Then we'll get our gear, a mathematical compass, and a terrain map. After that, we'll learn how to actually find the bottom. First, in a big open field, and then when we have to deal with tricky fences. We'll even uncover a special cheat code, a type of landscape that guarantees we can't lose. And finally, we'll learn the step-by-step instructions for the walk itself, the famous gradient descent.
All right, first things first. Before we take a single step, what are we actually looking for out here in this mathematical world? What does best really mean?
Okay, take a look at this. This visual gets right to the heart of the biggest challenge in optimization. Our hiker could easily wander into a little dip in the terrain and think, yes, I found it. This is the bottom. But that's just a local minimum. It's lower than the ground immediately around it, for sure. But look over there. See that much deeper valley? That is the global minimum, the true lowest point in the entire world. Finding that, well, that's the real prize.
So, to navigate this tricky landscape and not get fooled by those little valleys, our hiker needs two incredibly powerful tools. Just think of them as your compass and your terrain map. Our compass is called the gradient. Now, it's a vector, which is really just a fancy word for an arrow. And this arrow is amazing. It always points in the direction of the steepest uphill climb. It's built from things called partial derivatives, but all that means is it measures the slope in every possible direction, north, south, east, west, and combines them. So if the gradient points straight uphill, what do we do to find the bottom? Right, we just walk in the exact opposite direction. It's that simple.
Okay, so our second tool is the Hessian. If the gradient tells us which way is up, the Hessian tells us about the shape of the hill we're standing on. It's our terrain map. It's made of second derivatives, which just means it tells us how the slope itself is changing. Is the ground curving up all around us like a bowl? That's what we call positive curvature. Or are we on a tricky saddle point where it curves up one way but down another? The Hessian reveals all these critical details.
All right, we've got our tools. Let's imagine we're out in a wide open field. No fences, no boundaries. How do we know for sure, mathematically prove, that we've hit the bottom of a valley? Well, it turns out there are two key tests we have to run. First, the first-order condition. The ground has to be perfectly flat. Our gradient compass needs to read 0. Makes sense, right? If it pointed anywhere, that would mean there's still a downhill direction we could go. And second, the second-order condition. The ground has to curve upwards in all directions, just like the inside of a bowl. This is what positive semi-definite means. It ensures we're actually at a minimum and not, say, at the top of a hill or on one of those weird saddle points. Let's make this real with a super simple function that describes a perfect bowl shape. First step, we calculate the gradient, and we figure out where it equals 0. And as you can see, that only happens at one single spot, the point 0, 0. So test number 1 is a pass. Next up, we calculate the Hessian, our terrain map. Now to check if it's curving up like a bowl, we look at something called its eigenvalues. You can just think of these as the main curvatures of the surface. Since they're both positive, that confirms it. The ground is curving up in every direction. Test 2 passed. We've just mathematically proven that 0, 0 is the one and only bottom of this bowl.
Okay, that was the easy mode. But let's be honest. In the real world, our hiker is almost never free to just wander wherever they want. There are always rules, there are always boundaries.
So, a constraint is basically like a fence our hiker has to walk right alongside. And do you see the problem here? The true bottom of the valley. It's not even on the path. The lowest point our hiker can possibly get to is what we call the constrained minimum. And here is the absolute key takeaway. At that spot, the ground is not flat. The gradient is still pulling us downhill trying to get to the true minimum, but that fence is holding us back. This creates a whole new puzzle for us. If our number one rule, that the gradient has to be 0, is now totally broken, how on earth are we supposed to find that minimum point?
The solution is this absolutely beautiful idea called Lagrange multipliers. The intuition is fantastic. At that perfect spot on the fence, the pull from the landscape's gradient, which is desperately trying to go downhill, has to be perfectly balanced by a push from the constraints gradient, which is forcing us to stay on the path. It's an equilibrium. The two gradient arrows become parallel, pointing in perfectly opposite directions. It's so clever.
And what about for problems that are even more complex? Like, what if you don't just have to stay on a path, but you have to stay inside a whole fenced-in area? For that, we level up to something called the KKT conditions. Just think of them as a more detailed, more powerful set of rules. They include that Lagrange idea of balancing forces, but they add extra conditions for handling all the possibilities, like being right up against the fence or just chilling in the middle of the field.
Phew. Okay. After all that complexity with fences and balancing forces, what if I told you there's a special type of landscape out there? A landscape where a hiker's job becomes incredibly, almost trivially simple. A landscape that comes with a built-in guarantee of success.
Welcome, my friends, to the wonderful world of convexity. A function is convex if it's shaped like one single perfect bowl. That's the whole idea. No other little valleys, no bumps, no tricky spots to get trapped in. You can test it this way. If you draw a straight line between any 2 points on its surface, that line will never ever dip below the surface of the bowl.
And this simple bowl shape gives us what might be the single most powerful idea in all of optimization, the convex guarantee. Here it is. In a convex world, any local minimum is also the global minimum. Just let that sink in for a second. If our hiker finds what looks like the bottom of any valley, they can stop. They're done. They've found the bottom. There is nowhere lower to go. This is an absolute game changer, and it's why so many people in engineering and data science work so hard to make their problems convex.
Okay, so we've covered all the theory. We know the goal, we have the tools, we know the rules, and we even have the cheat code. So now let's get practical. How does our hiker actually, walk? How do they take each step down the mountain? The algorithm is called gradient descent, and the idea behind it is just beautifully simple. Here's how it works. You start at some random point on the hill. You pull out your compass, the gradient, to see which way is steepest uphill. Then you just take a small step in the exact opposite direction. You land at a new spot that's a little bit lower, and then you just do it again, and again, and again, repeating the process until you finally arrive at the bottom. That small step size, by the way, is controlled by a little knob we call the learning rate. Let's watch it in action, just once. Let's say we want to minimize the simple function f of x equals x squared. We know the bottom is at 0, right? Let's start at x equals 2. The gradient is 2x, so at our starting point, the gradient is 4. Let's use a learning rate of 0.1. Our little update rule tells us our new spot is 2 minus 0.1 times 4, which is 1.6. Look at that. In one single simple step, we've already moved from 2 much closer to our goal of 0. So let's pull it all together and just look back at the trail we've blazed. We started by equipping ourselves with our essential tools, our gradient compass and our Hessian map. These tools allowed us to understand the rules of the road, the optimality conditions for finding the bottom. They helped us navigate both open fields and tricky landscapes with fences. And finally, that amazing compass gave us the secret to the walk itself, the simple, powerful algorithm of gradient descent.
And just like that, our journey is complete. You now have a really solid mental map of how optimization works. You get the goal, finding that minimum. You understand the tools, the gradient and the Hessian. You know how to handle fences. You understand the magic of that convex guarantee. And you know the simple, elegant algorithm that powers so much of our modern world, from finance all the way to AI.
And this leaves us with a really fascinating question to ponder. We've just mastered the mathematics of finding the best possible solution to a defined problem. But how does this actually connect to artificial intelligence? How does a machine take this whole process and use it to learn? That is a fantastic story for another day.